First of all, I thank Dr. Jin-Young Park for the invitation, and it's my first visit to KITE, so I'm very pleased to visit here. Okay, so I will be talking about the generalization of the ample divisors. So in this talk, the variety X will be smooth, projective variety defined over some algebraically closed field of characteristic 0. Okay? So, and later I will allow some singularities on the varieties. And so on the variety X, we have divisors. They are the linear combination of codimension 1 subvarieties. But in this talk, the coefficients will be in integers or rational numbers or real numbers. Okay. So first, let's recall the definition of the ample divisors. So we say D is, so let's start from the integral divisors. So on G divisor, D is ample if the global sections of MD for some positive integer and define on embedding of X into some projective space. Okay, so this is a standard definition of ample divisors. But as you see here, this definition naturally extends to Q divisors. But if you have an R divisor, if this is R divisor, so we say an R divisor is ample if D is the linear combination of the integral ample divisors. If D is Ri, Di, Ri are positive real numbers and Di are ample G divisors. Okay. So we have ample R divisors. So we want to generalize this ampleness and study them. But before that, actually there are many conditions that characterize the ample divisors. So I will list 3 of them in this talk. The first one is the condition on the base locus. So the first one is the non-ample locus. D of D is empty. Empty. Of course, we have to define what this is. Okay. So if D is a Q divisor, then we can define something called stable base locus. It is defined as the intersection of all the usual base locus of the integral divisors, and it is a positive integer such that MD is a Z divisor. Okay? So this is called the stable base locus because this is actually the base locus of some So there exists some integer m0 such that this is equal to any. Okay. So there is such integer m0. That's why this is called the stable base locus. Okay. But we need to define this base locus for R divisors. So B plus, and this is called the non-ample locus. Ample locus of D, and it is defined as the intersection of all the stable base locus of D minus A, where A is ample, such that D minus A is a Q divisor. Okay, so here D is an R divisor. Okay. So you take all such intersections. Okay, so this is R divisor, but here we have Q divisors. Okay. But again, in fact, you don't need infinitely many intersections. And there is an ample divisor which stabilizes this intersection. So actually, there exists some ample A such that D is Q and this is equal to this intersection. Okay. And this base locus has many nice properties compared to this usual stable base locus. So so I list some of the properties. So first one is, as the terminology says, B plus D is empty if and only if D is ample. Okay. And the second condition says B plus D has no isolated points. Okay. So this means if I say dimension B plus D is less than or equal to 0, this means B plus D is empty because it doesn't have any isolated points. Okay. And one more nice property is that this base locus only depends on the numerical class of D, but this doesn't in general. Okay. B plus D depends on the numerical class of D, N1 XR. This is the divisors up to numerical equivalence class. Okay. So this condition is actually equivalent to dimension B plus D is less than or equal to 0. Okay. So this is one condition that characterizes the ample divisors. Okay. I'm sorry.
Is that why you define the R divisors like this?
Why we use R divisors?
Yes. Why?
Because we want to work in this R linear space, and we want to. So actually, it's very useful in the minimal model program because when you study the pairs, later I will say something about this pair, but some inductive purposes, sometimes we must use R divisors. For example, if you want to talk about the Zariski decomposition, sometimes you must have R coefficients. So, okay. So maybe I will say something about this later. Okay. And second condition is actually well known. It's due to Serre. So D is ample. So for now, D is a G divisor or Q divisor is ample if and only if for any coherent sheaf F on X. I'm sorry.
Why do you want the dimension as input, which is natural?
What? I'm sorry.
That's the input, which is not input.
There is a reason. Actually, I will relax this condition later on. So I'm sorry. So yeah. Okay, for any coherent sheaf f on x, there exists some integer m0 such that hi x xmd is 0 for any m0 for any I greater than or equal to greater than 0. Okay, and of course this condition also makes sense if D is a Q divisor. Okay, but for R divisors again, maybe we don't need to define for R divisors. So anyway, so this is well known. This is even in Hashon's book. Okay. 3. And the third condition is relatively new. It's due to the Fernet, Alex, Kronia, Lazarsfeld. It's in the paper published in 2007. Okay. So let's say D is a Q G divisor, G or Q divisor. Okay. So if D is ample, so if D is ample, as we saw here, hi x md is just 0 for large M for any I greater than 0. Okay, so because this is 0, if I put MD where D is the dimension of X, because this is 0, if I put things like these, it's still 0, of course. But they want to see if this is true, if the converse is still true. Okay. So let's use this. So to study the converse, so Alex Kronia defined the following function. It's called the asymptotic cohomology function. H hat I xd. So this is defined as lim sup hi x. So here, if I write MD, it means OX MD. Okay? MD DI. So he defines such function.
Throughout,
Sorry.
X is always smooth projective?
Yes, for now, yes. Okay? So he defined such function. And he discovered that HIXD only depends on the numerical class. So if you put 0 here, it may be familiar. It's just the volume function. So this is a generalization of the volume function. Okay. So HI hat depends on the numerical class, and it extends uniquely to a continuous function. HI hat X and 1R, 2R non-negative. So there is a unique such function, which any D, yes. So as I said, if this is 0, it's just a volume function. And we know that volume satisfies these conditions. And what they proved was the following theorem. D is ample if and only if HI hat XD prime is 0 for any D prime sufficiently close to D. So this vanishes not just at D. This vanishes locally near D. Okay? So this is the converse of the statement there.
So what is the difference
So if you put, so you may put here the class. So this is a finite dimensional space. So you can take an open neighborhood.
In the sense of topology.
Yes.
Okay. There is open subset where this is locally.
Locally, yes, yes. Okay. Of course, for any I greater than 0. Yes. Okay. So here we have 3 conditions that characterize the ampleness of the divisors.
Let me just
So, yes.
So here, when you plug in D for H hat, you allow the rear. I don't know what.
This is a Q divisor, Q or Z divisor. But Alex Kroner proved that this actually extends to
okay.
the I.
Okay, so you extend.
So here you may put R divisors. Okay, so here we have 3 conditions.
Here D prime is going to be actually Q divisor or actually.
Any R divisor. It's any.
Because it is extended. No?
Yes, yes. It's extended function. Okay. So now we want, as I said, we want to generalize the ampleness of the divisor. So how? So it's easy actually. So as he pointed out, you just need to change this part. So this 0 part to K from 0 to D minus 1, where D is the dimension of X. And here you change this to K between 0 and D minus 1, and here again. Okay. So this way you have 3 generalizations of the ample divisors.
This theorem coming from continuous and the openness of empty.
This theorem.
But I don't know which one is easier to prove, continuous or
Which continuous property?
you said that this function is continuous.
So it actually comes from the openness of the.
That just from the openness, and then that is the.
Okay. So here is the definition. So 1 prime. D is numerically K ample if dimension B plus D is less than or equal to K. 2 prime. D is cohomologically K ample if HI X. So you may have the coherent shape here, but I'll just write MD is 0, I K M sufficiently large. 3 D is asymptotically K ample if HI hat XD prime is 0 for all D sufficiently close to D for any I greater than K.
Characterized as asymptotically zero.
Yes. So if K is 0, they all coincide as the usual ampleness. So 0 means the usual ampleness. Okay. But if you relax the conditions here, they no longer coincide. So here K is between 0 and the dimension of X minus 1.
But what if you're choosing NEF and big divisor?
Yeah, that's actually the main theorem. If NEF and big, they all coincide.
But NEF and big, then you can find the ample divisor which is the limit. But this cohomological condition is 0 for every ample divisor. It looks like the network division
Actually, that's the main theory. So I will say, I will prove that if D is NEF and big, they all coincide. And they have some common properties. The first one is, I already mentioned here, but this function depends only on the numerical class. But in fact, all these three depend on the numerical class. The numerical class. Okay? And 2, just like the usual ampleness, they satisfy open conditions, open property. Okay. And if D is K ample, if any of these senses, then RD is also K ample for any R greater than 0. Okay. And now the convexity. the numerical K ampleness is convex. That means if you add two K ample divisor, numerical K ample divisors, then the sum is still numerical K ample. But the cohomological or asymptotic K ampleness is not convex in general. In general. Because there is a theorem by Totaro which says that D is D minus 1 ample. Sorry, here. He only studies the cohomological K. So D is cohomologically D minus 1 ample. If and only if D is in D is in minus effective complement. So this means so in N1 the pseudo effective cone is strongly convex. So this says first you take the minus and you take the complement. So this part is the set of D minus 1 ample divisors. Okay, so as you see here, it's already not convex. Okay? So if you add these two divisors, it's not D minus 1. Okay? And there is an important theorem mainly by Kronia, which says that numerically K ampleness implies cohomologically K ample. And by definition, this implies asymptotic K ample. Okay. So he proved this part, actually. And this part is by definition. But the converse is not true. This is not true in general. There is a counterexample. And so I write this way. But this way is unknown. There are no examples of divisors which are asymptotically K ample but not cohomologically K ample. But this part is true for toric varieties. So, and I define one more. I define some cones in N1. Okay, so it's definition. So amp K is the set of numerical K ample divisors. Okay, so D in N1, D numerically K ample, and H amp K is the D cohomological K, and H hat amp K is the asymptotically camp. Okay. And by this theorem, this cone is contained in here and this cone is contained in here. Okay. And as I said there, if K is 0, it's the usual ample cone. Okay. So let's summarize here. So you have amp 0, amp H amp 0, H hat amp 0, and you have amp K, H amp K, H hat amp K, and the biggest one is amp D minus 1, H amp D minus 1, H hat amp D minus 1. Okay. So you have many cones in N1, but many people only study ample cone and effective cones. And we know that if K is 0, it's just the ample cone, usually. And we know that this is, in fact, the big cone, which is defined as the interior of the pseudo-effective cone. Okay? So actually, these are subcones of the big cone. Okay? Because these are contained in here. But we don't know if these are contained in big cone or not. Okay? So I want to, for some reason, because later I want to run the minimal model program on big divisors. So I will restrict everything on the big divisors. So if H amp K B means H amp K intersection big. Okay? This is coming from the notation in cone conjecture. So if I put B here, then now everything is contained in big divisor, a big cone. Okay. So you can also define H hat amp KB similarly. And my first question was if this cone is contained in here or not. This cone is contained in here or not, so that you have chain of cones. That was my first question, and I could prove that lemma. So if you restrict these again in the NEF cone, H amp K minus 1 XB is indeed contained in amp K X. Then this holds. So you have to restrict again in the NEF cone. Then this cone is contained in here, this is contained in here, and you have a chain of cones.
In FX means you are taking intersection with NF as well?
Yes, that's all, yes. So, yeah, in NF means NF. Okay, so this is the first theorem of mine. Okay, see. So I already announced the main result, but for nef and big divisor D, so all the three notions coincide, or the K amplitudes coincide. The proof is quite easy. It's not difficult at all. So this is only proof in this talk. But so you have three notions of K partial amplitudes. First one was numerical K amplitudes. But this implies cohomological K amplitudes. And this implies asymptotic K amplitudes. So we only need to prove that this implies this. This is the main part. So let's assume that let D be so D is already nef and big. Okay? So let D be asymptotically K ample, but not numerically K ample. Okay? Asymptotically K ample, but not numerically K ample. Okay? Then what happens? So let's draw some pictures. So this is a nef cone. And this is H hat amp K. Okay? So as I said, B is asymptotically K ample, so it's contained in this cone. But it's in nef and big. And if D is already ample, this notion coincides with this. Okay? So we may assume that D is not ample. So that means it's only nef. So it's somewhere here, D. Okay? So we may assume that B plus D is not empty. Okay? And one property of the non-ample locus was there exists some ample divisor A, such that the stable space locus of D minus A is equal to the non-ample locus of D. So we subtract some small ample divisor. So if you subtract, it goes outside. So this is D minus A. So, and I will denote this by D prime. Okay? D prime. And the idea is this. Because there is a gap, you may find some ample divisor, A, such that it should be bigger. Such that if you add A to this divisor, it becomes ample. But if you add the half of A, it's not ample. So you may find such divisor. This is A, but this is 1/2 A. Okay? So there exists, so I already used A, so A prime. A prime. Okay? So there exists some ample divisor A prime, such that D prime plus A prime is ample. But D prime plus 1/2 A prime is course, it's not ample, but we may still assume that. So here we use this lemma. D is let me write the conclusion first. It's not k minus 1 asymptotically. Okay, ample. Okay. Because as I said, D is already not. So here, D is not numerically k ample. But it's not even contained in here. That means it's not even asymptotically k minus 1 ample. So that's why we have this condition. So D prime is not even asymptotically k minus 1 ample. Okay. Because it's here. And the rest is easy. It's just we just use the long exact sequence of cohomologies. Okay. So let B be a subscheme of codimension 1, which is given by the zero locus. Given as the vanishing locus of some section of MD prime large M. Then we have this exact sequence. OB OX, sorry, minus MD plus OX OB. And you just need to tensor this with M to D prime A. So this is the main part. Then what do you get? 0 OX M D prime A prime 2 OX M 2D prime A prime OB and you have something. Okay. And if you look at the long exact sequence, this is the last step. Okay, HK X M D prime A prime HK X M 2D prime A prime HK V something to HK M D prime plus A prime and so on. Okay. And D prime A prime is ample as I have there. Okay. So if M is sufficiently large, these are 0. So these two are isomorphic. But V has codimension 1, so this cannot grow like M D minus 1. But the condition on 2D prime A prime is what? It's asymptotically K ample, but not asymptotically K minus 1 ample. So that means if M is sufficiently large, this must grow like MD. So there is a contradiction. Okay. So I proved that if D is nef and big, then the three notions of partial ampleness all coincide. Okay. So this is the main result. But so my main area of research is the minimal model program. So after I found this result, I applied this result to the MMP. Okay, so apply application to MMP. So, but let's recall what MMP means. So you just need one statement. Okay, so X is still a smooth variety, but so we studied a pair. B is some pair. B is some divisor. Di, Bi, and Di some real numbers between 0 and 1. It's called the boundary divisors. Okay, and this will have some KLT singularities, but you don't need to worry about the singularities. Okay, so singularity is KLT, and K plus B is big. And big means, as I said, it's in the interior of the pseudo-effective form. Okay. Then there is a famous result by BCHM. There exists a birational map from X to Y such that KY plus, let's denote this by F. F push forward B is NF. And this will still have the same singularities. It's KLT. And there is actually one more condition. So if you just have these two conditions, it's called such pair Y F push forward B is called the minimal model. But you have some starting model. So we want to talk about some minimal model of the initial model. So we have one more condition. It's XB less than or equal to AE YF. So here A is the log discrepancy, and E is so here for any E, prime divisor E on X, which is exceptional over Y. But actually, you don't need to worry about. You don't need to know what this means. This the third condition just means the singularity is improved. Singularity is improved. Okay. So in other words, X, Y. So you take some common resolution. Let's notice by P and Q, and P pullback K plus B. Let's start from KW. KW plus B, P pullback K plus B plus E. So to find the singularity of the pair XB, you look at this exceptional divisor. Okay, so KW, BW, Q pullback KY, E prime. So if this is small, then it has a bad singularity. If it's big, it has a good singularity. So as I said, the singularity is improved. So that means this is bigger. Okay? So that means, in other words, P pullback K plus B, Q pullback KY plus BY plus some N. So N is, in this case, effective. So we will use this condition. This becomes important. Okay. So this is what MMP means. Okay, so if I say run the minimal model program on the pair, then it means you find this mode. So how do you apply MMP? So first theorem is so let's say we are given a pair like this, KLT, K plus B is big. Then if K plus B is asymptotically K ample, then so is KY, BY. So this notion is MMP invariant. Okay? And the proof is easy. First you start, so you look at the asymptotic cohomology function, K plus BY, K plus B. And there is a result by Kronia, which says that this asymptotic cohomology function is invariant on the pullback. It's W P pullback K plus B. And this is also equal to HI hat W Q pullback KY plus BY plus some effective divisor N. So I have to admit that in the talk I gave in Kunsan last summer, I said that W KY, this is just equal to this, only because N is exceptional. But actually I found there is a counterexample which the statement is not true. So later I discovered that this is actually the Zariski decomposition. So the correct argument is this. So effect. This is actually also theorem by me. And if D plus B plus N is actually it's not the usual Zariski decomposition because the dimension is higher. So it's Fujita Zariski decomposition. Then H high hat XD is H high hat XT. So we have to use this fact actually. So this. So before this, so according to this fact, this is the positive part of the Zariski decomposition, and it preserves the asymptotic cohomology function. And now again, use the result of Kronia. Hi at y, ky, by. Okay. So this proves the MMP invariant property of the asymptotic cohomology for adjoint divisors. And not just this is MMP invariant. Actually, if you are given the same pair XB, then for such pair, the cohomological numerical cohomological asymptotic asymptotic K-emptiness of. I'm sorry?
Where do you use your previous theorem to
Previous.
your previous theorem? So this is one of the application of your previous theorem. So will you use the net and peak condition?
Here we use the NF and B condition.
So here you, in this proof you do not.
you don't. I don't. This is not the corollary of the previous result.
But will you use ky plus by as net?
NF here, because
For
Zariski decomposition. Yes, because this must be NF, and if D is big, P is big. Okay. MMP is MMP invariant. And the proof is also easy, because let's say K plus B is numerically or cohomologically Km. Then this implies the asymptotic Km. But if we run the MMP, then Ky plus By is also asymptotically Kemp. But this is Nef and big. So if I use the previous, not this one, the previous theorem, this is if and only if Ky plus By is numerically or cohomologically Kemp. Okay. So if this divisor is numerically Kemp, then Ky plus By is still numerically Kemp. And one last corollary says that if X is Fano, or actually Fano type, or Mori dream space, then for big divisors, the three notions of partial emptiness coincide. So, and this answers a question by Totaro and Demari. They asked if the notions coincide on Fano varieties. Okay. And as I said, there is a result which says that this is true for toric variety, projective toric variety X. So this generalized the previous result. Yes. So the motto is, as long as you can run the minimal model program, the three notions always coincide. Because on these varieties, you can always, so in this, for Mori dream space, I mean DMMP. On Fano or Fano type varieties, you can run the minimal model program. So that's why these three notions coincide. Okay. And so I'll just finish with one question. One question is, so we have three cones, MK, H, MK, H hat, MK. So it's a question by total rational polyhedral for Fano X, Fano variety X. So this is the question. So, and if K is 0, D minus 2, D minus 1, the answer is yes. But for the rest of the cases, it's unknown, but I expect that this is true if you use some result called geography of minimal model program. Okay. So I think it's yes for the rest of the cases. But, so I'm studying this case for now. Okay. So yeah, so I stop.